So this section is a bit of extra material on rational functions we're going to look at. There's going to be four major objectives: to understand the general shape of rational functions, to identify characteristics of rational functions, to discuss end behavior and graph horizontal asymptotes, and to define discontinuity and graph vertical asymptotes and holes. Some terminology that we should know. A rational function is any function that can be written as a ratio of two polynomial functions. So for example, something like this: f of x equals x plus 4 over x squared minus 7. That would be considered a rational function because this is a ratio and these are both polynomial functions. End behavior is really the behavior of the function as the independent variable, in our case x, tends toward infinity and negative infinity. So it really means what happens to the graph as the value of x gets really, really big or really, really small. Finally, discontinuity is when a function is not continuous at a specific point. So for some reason there's some sort of a gap in the graph or a hole or an asymptote. And finally, let's define asymptote. An asymptote is a line such that the distance between the curve, meaning the graph, and the line itself approaches zero as they go to infinity, as they tend to infinity. So we'll start with domain, vertical asymptotes, and holes of rational functions. This will be the first of four sections on this. So the general shape of rational functions are seen right here, okay, where you see these dashed blue lines. Okay, and as we can see in the three examples here, they're unique looking functions. They're different than what we're used to. And the dashed blue lines, they're not actually points on the function, but they're called asymptotes. Asymptotes. And the idea is that the function itself has a tendency to get larger and larger and larger, but it won't cross that asymptote. It'll tend to go toward it and toward it and toward it as this continues upward. Or it'll get closer and closer to this asymptote. Or here we can see the red curve getting closer and closer and closer to the horizontal asymptote. Whereas maybe this red curve here, when they go to the right, gets closer and closer to this vertical asymptote right here. Okay? Now, they're really just imaginary lines. They're not really part of the graph. And sometimes we have diagonal lines, and those are called slant asymptotes. They really act as boundaries. And what we can see is that not all rational functions have both x and y intercepts. We can clearly see that. Here, for example, there are no x-intercepts. This graph will tend to go closer to the x-axis, and so will this one, but they're not going to cross it because the x-axis happens to be one of our horizontal asymptotes in this function. Here, there's no y-intercept because the vertical asymptote, which is the y-axis, acts as a boundary. This curve gets closer and closer and closer, and this one gets closer and closer, but it doesn't actually touch it. So let's take a look at the idea of a domain and a vertical asymptote. So first, remember that the domain of a function tells us the values that the independent variable, traditionally x, can take on. So when we think about rational functions, we have to look for values of x that make the rational function undefined. Okay, so let's look at example 1 here. Determine the value of x that make the rational function h of x undefined. Then use this information to make a conclusion about the domain of the function. Then plot h of x, meaning on your graphing calculator, to see what this looks like. So start. We have our function here. What values would make this undefined? Well, it becomes the question, what values make this denominator equal to 0? So what we do is we go ahead and just set it equal to 0. And we see that when x is equal to 2, if you put a 2 in here at the bottom, this becomes 0 or undefined. So what this means is that x can be all values except for 2. Another way of writing this is that x goes from negative infinity all the way to 2, and there's a gap in the graph, and then it goes from 2 to infinity. But when x is equal to 2 on the graph, it is undefined. And let's see what that looks like here. So what we'll do is, to figure out the points, is we'll look at the graph from the left and from the right of x equals 2. So if we look at it from the left, we'll see that as the value gets larger and larger and gets closer to 2, what's happening here? Well, h of x is getting smaller and smaller and smaller, or it's going to negative infinity. And that's this part of the graph. As the x-coordinate gets closer and closer to 2, we see the graph diving off as it gets closer and closer, and it's going to continue to go down. And it's never going to cross this asymptote, but it's going to get closer and closer, and it's going to go down to negative infinity. So if we kept going with this, like 1.999 or 1.9999, that value is going to get larger, but larger in the negative direction, meaning it's going toward negative infinity. From the right of the graph, we'll notice that what's happening here is we look at the values here. These values are getting larger in the positive direction, and that's this. As this gets closer, the value of the function gets larger and larger and larger, but it never crosses the vertical asymptote. It just gets closer and closer toward it. And remember that when you plug in 2 for x, it is undefined, and that's this right here. There's no definition of the function x equals 2, which is why this dashed line exists, showing that the function cannot actually have a value when x equals 2. So as a conclusion, what we can say is that we can see that the value of the independent variable that causes the denominator to become 0 are not included in the domain. And this means that there's a discontinuity there, such as a vertical asymptote we've seen here. Okay? There's another type of discontinuity that we'll look at now, and that's called a hole. So let's take a look at that. So in example 2, what we're going to notice is we're going to see that our denominator here is actually quadratic in nature. So for this problem, we're going to take a look and we're going to see, well, this can be factored, right? If we want to figure out what values make it 0. So we start by setting the denominator equal to 0. So set this equal to 0 here. Factor it, giving us x equals 6 and x equals negative 2. Well, these two quantities right here make the function undefined. So those are clearly discontinuities. Now the question is, are they vertical asymptotes or are they holes? To figure that out, what we actually end up doing is this. We take the value that would make it undefined and plug it in actually. And if you plug in a 6 up here, you're going to plug in a 6 here and in these locations. And you're going to get 16 over 0. Well, that's clearly undefined. So when it's undefined like this, or any number over 0, it's going to be a vertical asymptote. But when we plug in negative 2, and this should say g of negative 2 here, when we plug in negative 2 into the function, we're going to realize that we get 0 over 0, which in this sense, though, is called indeterminate. It's not called undefined, it's indeterminate. And what this happens is, what really is going on at negative 2? How is it indeterminate? What does that really mean? So one way to do that is to look at a table like we did before. So we'll get closer to negative 2 from the left. And we'll notice that as we get closer to negative 2, the y value gets closer to negative 1/4. And if we do the same thing here from the right, we get closer to negative 2. We're going to see that it also gets closer to negative 1/4. And these headings are switched. This should say right and left. We'll switch those two. But what we're noticing is this. We're noticing that it's getting closer to 1/4. Well, where does that, or negative 1/4, where does that come into play? If you take a look at this function, okay, and we factor it appropriately like we did earlier, we'll see that the x plus 2's cancel, leaving behind 2 over the quantity x minus 6. Now, if you take the 6 and plug it in, you're still going to get undefined. But if you take this negative 2 now and plug it into the function, or the simplified form, if you plug the negative 2 in, you're going to end up getting negative 1/4. Well, that's this quantity that it's getting closer to. So in this problem, we have a hole. And the value of the hole, or the hole's location, is at negative 2 comma negative 0.25. It's not part of the function, it's an open gap or an open circle. So we're going to take a look, we're going to see that right here at negative 2 comma negative 0.25, we have an open circle there showing that there's a hole at this location, or a discontinuity. A discontinuity simply means that if I were to continue along this path, I'd have to pick up my pen, hop over the hole, and continue. Just like here, I'd have to pick up my pen and then start back up at the top. So this vertical asymptote is also a discontinuity. So again, notice the vertical asymptote at x equals 6, but a hole at x equals negative 2. Make sure you're careful when you graph these on a calculator, because when you graph this and you look at negative 2 for the x value, it's indeterminate. And you're not going to see that. Okay, you're not going to see that on the actual graph. So as a conclusion, if the value of a function at a discontinuity is indeterminate, meaning it becomes 0 over 0, then there's got to be a hole there. And you could think of this as having the same factor in the numerator and denominator, simply canceling those factors and figuring out the height of the hole, or the location of that hole. So let's finish off with example 3. Determine the values of x that cause f of x to be undefined and then classify as an asymptote or a hole. So again, we're going to do the same thing. But let's factor the top and the bottom here so we can identify vertical asymptotes as well as holes right away. So factor in the numerator, we're going to get 3x times the quantity x plus 2. The denominator, we take an x out, leaving this behind, but then we factor this into x plus 5x minus 2. So as a result, we have the quantity 3x times the quantity x plus 2 over x times the quantity x plus 5 times the quantity x minus 2. So by inspection right away, we're going to see that x cancels and x cancels. So Well, what would cause this denominator to become undefined would be if x equals 0 from here, if x equals -5, or if x equals +2. Well, clearly, since the x is canceled, that means that x equals 0, we happen to have a hole. Remember, when the same factor appears in the top and the bottom, we have a hole because the function's value is indeterminate there. But at the other two locations, we're going to have vertical asymptotes. So the asymptotes are at x equals -5 and x equals 2. And we can see that in our graph right here. At -5 and at 2, there's our vertical asymptotes. Well, how do I find the value of the hole, or the location rather, I shouldn't say value, the location of the hole? I look at the simplified form, which is this. When I cancel this x with this x, this is the simplified form. Now we can plug in a 0 here. So if you plug in a 0 up top, you're going to get 6. And in the denominator, you're going to get -10. 6 over -10 is -0.6. So the location of the hole is clearly going to be 0, comma, whatever you get, which was -0.6. And there's the hole at 0, comma, -0.6.